Uhlir is going to present to us R&D in the Czech Republic on MSR and on future directions.
Yes. Okay. Okay. So this one. Okay. So. Thank you for your introduction, Mr. Chairman. Good morning, ladies and gentlemen. So my presentation will be about the current Czech R&D in thorium, MSR technology and future directions. I prepared this presentation together with my colleague, Vlastimil Juříček, sitting over there. We are working for Research Center ZESH, which is daughter company of Nuclear Research Center, which now has the name UJV. I don't plan to give the talk about some advantages of thorium and molten salt reactor technology, because this discussions are approximately 13 years over in Czech Republic, so we made the decision at the beginning of this century or end of last century. So outline of my talk will be about the arguments for R&D in MSR in Czech Republic. Yeah, existing R&D projects supported by the Ministry of Industry and Trade, because our company is private company, so we are doing our research only based on the contract with the government, with the Ministry of Industry and Trade. So about the development in reactor physics, structure, material and fuel cycle technology for MSR, and current status and future directions. Okay. So the decision to develop selected technologies of NSR system and to resume on the Oak Ridge effort from 60s was made in Czech Republic at the end of last century, and Ministry of Industry and Trade has been supporting our R&D program since 2000. So if you compare it, it was a year before Generation 4 International Forum chart. Also, our PNT program was at the beginning also based on the MSR technology, I mean as MSR incinerator, and fluoride pyrochemical partitioning. And in Europe, we were practically an exception, because most of other European countries focused on fast reactors and ADS system. Sense and background. So we realized that the basic principles of MSR were successfully verified in Oak Ridge, and that here is some problem with the verification, because of fuel cycle of MSR was not fully verified this time. MSR technology for us, we realized that it can be one alternative, because Czech Republic is a small country, and we await that it can be a bit problematic for so small countries to develop fast reactors and to deploy fast reactors. So you can imagine, yeah, fast reactors with content of fissile material more than 20%, so it's difficult for small countries, good for superpowers. So our main aims were to appropriately contribute to the knowledge of general area of molten salt reactor physics, core design, safety, structure, material, and thorium uranium fuel cycle, and to focus on R&D technologies applicable within this on-liner processing of liquid fuel. So Czech Republic is too small country to be able to develop some Gen 4 reactor system alone, yeah, completely. But we would like to be an important partner for final collaborative development of MSR in this case. So I guess I can go through this quite known picture about molten salt reactor. So molten salt is non-classical reactor system with typical fuel of fluorides of actinized dissolved in carrier melt. So I would like to focus on two important projects supported by the Ministry of Industry and Trade in last period. It was nuclear system Sphinx with molten fluoride salts-based liquid nuclear fuel. And subsequent project fluoride reprocessing of generation 4 reactor fuels, which were solved in Czech Republic in last period. So the first project covered practically the whole areas of MSR technology, but for sure we were limited by financial sources. So the project was solved by a consortium of institutions and companies, including Nuclear Research Institute, ThEC, Škoda Nuclear Machinery, Energoviskum, private company, small private company, and also the Faculty of Nuclear Sciences and Physical Engineering of Czech Technical University in Prague. The second project, fluoride reprocessing, was solved only by the Nuclear Research Institute in ThEC. We also participated in selected Euratom projects devoted to MSR, like MOST, Alicia, and some small participation is still in EVOL project. And we were relatively active in System Steering Committee as representatives of Euratom in Generation 4 International Forum. Our nuclear system Sphinx, this project, which was divided into several work packages. So you can see here the work packages of MSR core and primary circuit, work package 2 fuel cycle technology, then experimental MSR core and its control system, secondary circuits and components, structural materials or development of nickel alloys here, and system study of Sphinx. And also it was very important for us and practically the main effort experimental program. Okay, so I would like to give you some short information about some results from Sphinx project. We focused on the verification of some neutronics of molten salt. Therefore, we had to develop some modified computer codes for calculations of neutronic characteristics of MSR system. Here the problem is that the fuel is moving in the system. So some codes for solid fuel, which is all the time inside the reactor, is not possible to use. Yeah. We focused also on some experimental measurements of neutronics. So in our LR0 reactor, we put some inserted zones in the center of the core. Then the classical VVR fuel, yeah, so light water reactor fuel, was a neutronic driver, yeah, for our measurements. So it was necessary to build these inserted cores. Here you can see some type of geometries, yeah, so graphical channel. At the beginning we started with lithium fluoride, sodium fluoride salt, but later on we continued with lithium fluoride, beryllium bifluoride salt. Here is some different geometry with several channels, graphite channels, and peripheral cylinder in graphite channels. This configuration. We also, we had to manufacture these inserted zones. Here you can see that the view into our reactor and the zone is then, this is, I try this. So the picture on the right, yeah, is inserted zones. It has the same geometry as one fuel assembly. Yeah, so and was in the center of the reactor for this measurement. For our measurement, we had to prepare the salt. So we focused also on the development of verification of liquid field processing, molten salt containing uranium tetrafluoride, thorium tetrafluoride. So in the left picture on the left, you can see some small blocks of flyby salt containing uranium tetrafluoride. Therefore, it's slightly green. Yeah, we filled it in the inserted zone. This blocks. On the right side, there is a picture of some small molten salt loops. So we manufactured several loops. Sometimes it was attempt, mistake, attempt, mistake, attempt, success. Yeah, so this is very small loop for corrosion tests, and it is in the box, in the heated box. So here we can reach the temperature till 800 centigrade about, and this loop is still in operation. Okay, so concerning the development of structural materials, it was impossible at the beginning to obtain Hastelloy N from Heinz company, because our wish was to buy tens or hundreds of kilograms, but the Heinz company was ready to support us either nothing or several tens of metric tons. So it was problematic for us. Therefore, we asked Škoda Nuclear Machinery and the company Comtess to develop a special nickel alloy moniker. It's relatively very similar to Hastelloy N modified. And we continued with corrosion tests, radiation and metallographic tests. So today, the Comtess company is able to produce it in relatively small quantities, so semi-pilot technology. Company Energovýzkum was focused and is still focused also on the design and development of some components. So now they have under development also the valves and impellers, and another company, it's a company named Mikko, focused on seals and flanges, yeah, so because it's also necessary for this development. Concerning the secondary circuit and the studies of fuel cycle, we also discussed this problem, and we also discussed the problems concerning the system studies. So it means if to focus also on the single fluid or double fluid system. So single fluid when fertile fissile materials together in one channel, double fluid or two fluid system when the fissile fertile materials are in separate channels. And we also discussed non-proliferation or physical protection aspects problems. So here I would like to show you some pictures how we prepared uranium tetrafluoride. So the preparation generally is easy for example for enrichment process before the step of preparation of UF6. But here there are very strong conditions to have UF4 completely without oxygen. Also our preparation of thorium tetrafluoride. So here you can see some relatively smaller chemical reactor. So we are able now to produce some kilograms during one batch process. Preparation of ampulla. So our in-core experiments with salt at the beginning with the salt at room temperature. yeah, was made not only in Nuclear Research Institute in Czech, but also at the Faculty of Nuclear Engineering in Prague. And the students here have approximately 7 years. Yeah, it was before 7 years ago when we started the program that here's some possibility to go through a topic, liquid fuel and molten salt reactor technology. So many students in Czech Republic obtained also this background. To the thorium breeder, I skip over this picture because it is, I guess, known for you. Concerning the fuel cycle technology, here it is important to realize that if you can see here the spent fuel online reprocessing, it doesn't mean that during the circulation the whole fuel must go through the reprocessing unit. No, only some small part, yeah, of the circulating fuel, which circulates through the reactor and heat exchanger, yeah, so only a relatively small part is piped into the reprocessing unit. And here are different conditions. Some elements must be extracted as soon as possible. Some elements are not so problematic. Yeah? Typically, protactinium must be separated as soon as possible. I explained later on. Yeah? And some other fission element, but not all. Yeah? So because the mission of online reprocessing of molten salt reactor is to keep the reactor in steady state conditions. Yeah? So necessary to keep away, yeah, this neutron poisons like xenon, krypton, later on lanthanides, and to extract freshly constituted fissile material. So I guess this reaction is known for you, so it's necessary to separate protactinium from the system and to protect it against neutron flux as soon as possible, to have some suitable breeding factor to achieve. So concerning the technologies possible for online reprocessing, here are mentioned. So generally those are fluorides technologies, theoretically fluoride volatilization processes, I mean fused salt volatilization, molten salt liquid metal extraction process, possibly electrochemical processes, gas extraction. In Oak Ridge it was known as helium bubbling. We focused on the electrochemical reprocessing of MSR in Czech. And we also focused on the handling with flybead, so it means with lithium fluoride, beryllium fluoride, so you can see that flybead is friendly also for ladies. Yeah. During our development of electrochemistry, so we realized that there is any salt which is as suitable for primary circuit as for online reprocessing. Yeah? So we handle this with this type of salt. So flybead, the problem is that flybead is insufficiently electrochemically stable. It's a problem of beryllium bifluoride. Therefore, we had to find some another mixtures. The best one concerning the stability is lithium fluoride, calcium bifluoride, but the problem is with relatively high melting point, yeah, over 600, yeah, 650. Yeah. We developed electrochemical separation processes for this type. The problem was because in fluoride molten salt media there was not existing suitable reference electrode. So we had to develop this reference electrode. So this summer I was very happy to hear and to see that our Chinese colleague are using also our design for in Shanghai Institute of Applied Physics. And here I have the table of evaluated redox potentials. Here it is, I guess, important, the result. You can see here that it is practically impossible to separate all elements from one type of salt. Yeah? From Flybe, it's possible to separate uranium from thorium, uranium from neodymium, gadolinium, samarium, europium, promethium, praseodymium, yeah? And so. But some separations are impossible. Therefore, we realized that the flow sheet will need to be some mixture of the electrochemical processes from different fluoride salts. We also realized that there's very strong mutual link between reactor physics and chemical technology in molten salt reactor technology. Eh? So what is important, you can read it, that instantaneous fissile power affects the capacity of online reprocessing, and that the rate of reprocessing has the retroactive effect on the quality and concentration of fissile material. The rate of protactinium removal affects the breeding factor of the system, and another interconnection between chemistry and reactor physics is based on the fact that the fission reaction, yeah, is oxidative process, which must be chemically compensated to keep reductive conditions in the fuel circuit to minimize corrosion of structural material, I mean nickel alloys. Yeah. So, and if we wish to maximize the breeding, then our task is not only to extract protactinium as soon as possible, but also to identify the main neutron poisons among fission products in the circuit. It can be done on the basis of their production rates and neutron capture cross-section. Yeah? So the knowledge was important for our flow sheet. So here I would like to show you our results and what should be what should be done. Yeah? So you can see that the most problematic concerning neutron capture and concerning poisoning effect is seen on here. Yeah? Okay, so it can be removed in impeller by a gas extraction, yeah, helium bubbling. But from the group of fission products dissolved in the Flybe salt, we should focus on three elements: samarium, neodymium, and promethium. Promethium, big problem for us, because promethium is not a problematic element for reprocessing from existing light water reactors due to relatively short half-life. Yeah? The problematic isotopes have lifetime about 200 days. So in the spent fuel, after 6-10 years of cooling time, that there is zero. Yeah, practically. So now we would like to open the discussion with people from MAIAC, how to obtain promethium for our further experimental work, how to verify the possibility to extract it electrochemically. Okay, so system studies core design was mentioned already here. There are two possibilities: one fluid system, two fluid system, sometimes called single fluid, double fluid system. In case of two fluid system, theoretically, the breeding factor can be relatively excellent, yeah, more than 1.1, yeah. But there is also the penalty. Penalty is lifetime of graphite. Here I would like to mention the mission. Yeah, in case of one fluid MSR online reprocessing design, so the extract neutron poisons and separate freshly breeded fissile material. Here I have some scheme. Yes, so. You probably know also some alternative schemes, yeah, proposed by our Russian colleagues or French colleagues from CNRS. So it's difficult to say what is the best. So it is necessary to verify it, yeah, and maybe that it will be changed either this approach, which is much more focused on the electrochemistry, or another approach much more focused on molten salt liquid metal extraction. In case of two fluids, separate channels for fissile fertile material. So here I have the scheme for fissile fluid. Yeah, so fissile fluid circuit here. Relatively easy, easier scheme for fertile fluid circuit. Here, the task is only to separate protactinium, and to current activities and future direction. So we made relatively nice measurements in core measurements of salt, but with wrong salt. We used natural lithium. So then, after several years of discussion between our Ministry of Industry and Trade and United States Department of Energy, ministries concluded agreement. This year, we obtained from Oak Ridge about 75 kilograms of enriched lithium fluoride, beryllium bifluoride, and we are now discussing, and we have under preparation the joint program, which will be focused as for FHR, that's US interest, and MSR. So at the beginning, it will be probably evaluation of reactivity coefficients for this type of salt. So to the conclusions, we have investigated selected areas of MSR system and thorium uranium fuel cycle technology, including reactor physics, chemistry, liquid fuel processing, online reprocessing technique, development of structural material and components, system studies, and future intentions. New program, which is scheduled for the next 3 years, is now under final preparation, and it will be based on the agreement between Ministry of Industry and Trade of the Czech Republic and US DOE, and will be focused on these two reactor system, FHR, MSR. And of course, we plan to be active in international collaboration. And because, as I mentioned, Czech Republic is a small country, we have only 10 million of people, so our sources are limited. So we would like to be some beneficial partners for other countries which are developing molten salt reactor technology. So thank you for your attention.
Thank you very much. Do we have questions? One question there. Mr. Ganesan.
I'm Ganeshan from BRC, India. Say, you mentioned about this two fluid separate system, fissile material and fertile material. But in the case of the unlikely event of the fissile portion alone getting heated, that would pose a positive Doppler coefficient. And there would be a time delay for the heat transfer to take place in terms of phonon transit time. And the negative Doppler effect will come with a time delay. So did you look at this possibility?
So I'm not expert in theoretical reactor physics. So maybe Vlastimil, if you would like to answer this question. But generally, for sure, we focused also on the theoretical reactor physics here. But our approach today, yeah, is to develop to go ahead, yeah? I mean, in existing knowledge. So maybe Vlastimil will be able to answer this question.
Yes. See, when the temperature increases, you get the Doppler effect because the cross-sections, effective cross-sections change and the reaction rate increases with temperature.
Yeah.
If the capture dominates, the Doppler coefficient is negative. But if you have pure fissile material, you have fission cross-section dominating over capture in the fissile, and the Doppler effect becomes positive for plutonium or U-233 and so on. So we have dismissed many concepts whenever positive Doppler coefficients occur. So I would like to know whether you have investigated this possibility of differential Doppler coefficient coming into play.
I remember it was also studied. In fact, so here are also the problems. For example, loss of fertile salt Yeah, so it also completely changed the conditions, yeah, including the K effective, yeah. So, but I'm not expert in this area, so very sorry. So
maybe you have to look at it. Yeah.
Yeah.
Okay. Well,
Thank you.
could you bring a mic to that gentleman there?
Yes.
Yeah, go ahead, please.
Yes, Chairman. Mr. Jain, I know you are one of the experts in this area of molten salt technology. But my question is not this fuel cycles in molten salt technology. In general, the question is towards all the people who are interested.
Speak closer to your mic, please.
To the people who are interested in developing this molten salt reactors, whether it is a thermal reactors or first reactors. My basic question is, you see this, when you're talking of the molten salt reactors, the reprocessing is an inherent to the system. Okay. Now, when you are looking for developing this technology and transport to this technology to a developing countries, don't you think that sensitive nature of the reprocessing technology will come in the way of developing of such a technology?
So, concerning the future development and mastering of this technology, so we must take into account that it is extremely difficult technology. It is extremely difficult technology, and there is for small countries, not superpowers, there is one advantage. So the content on fissile material in fuel circuit is 0.2, 0.3% only. Yeah, so that's one. But concerning to mastering of this technology, I'm afraid that it will be difficult for some countries which have no good technological background.
But I think this is interesting. This is a point we might come back to in the roundtable discussion. Is that means probably this calls for some kind of international collaboration, because one single country maybe can take care of a single item, but I think in view of the complexity of the system, I think cooperation is certainly a must in this area.
For sure, for sure.
All right. Now, I think we're running out of time. I would like to stop here, close the session. We will come back to this type of discussion on Thursday during the roundtable discussion. We have foreseen plenty of time to have those type of discussions. So the discussion is not